Hello, my name is GRV.SRIRAM. I am from CSE Data Science Department. My roll number is 24951A6747. The course title of this presentation is Operating Systems. And the topic title is Dependability Analysis for Fault Tolerant Computer Systems using Dynamic Faults Graphs. Dependability Analysis for Fault Tolerant Computer Systems using Dynamic Fault Graphs. This presentation explores the critical role of dependability analysis, specifically using dynamic fault graphs (DFGs) in the design and evaluation of fault tolerant computer systems. The imperative for robustness. Why dependability matters. Fault tolerant systems. First one, the critical systems. Modern critical systems in aviation, defense, and finance demand near zero downtime, where even minor interruptions can have severe repercussions. And the second one is the continuous operation. Fault tolerance ensures systems maintain continuous operation despite the inevitable occurrence of hardware or software faults, safeguarding against disruptions. Catastrophic consequences. System failures can lead to catastrophic outcomes, including significant safety risks, substantial financial losses, and irreparable data corruption. The challenge modeling complex fault tolerant architectures. Fault tolerant systems rely on extensive redundancy and sophisticated recovery mechanisms, making their behavior inherently complex. Dependability and next, the dependability modeling must accurately capture these dynamic behaviors and integrate interactions between various faults. Introducing dynamic fault graphs, DFGs. Dynamic fault graphs are advanced graph-based models specifically designed to represent system components and their potential fault propagation paths. They capture temporal and causal relationships dynamically, offering a significant advantage over static fault trees. DFGs enable a detailed analysis of fault sequences, including recovery processes and system reconfiguration events. How dynamic fault graphs work. A visual example. Nodes with a DFG typically represent individual components or specific fault states. Edges illustrate the pathways of fault propagation throughout the system. Dynamic transitions are crucial as they model the occurrence of faults, their subsequent detection, and the steps involved in system recovery. By visually representing before and after fault injection, DFGs clearly reveal the system's resilience pathways and how it handles various failure scenarios. In this diagram, you can clearly see that the flowchart here. First, the component A failure to fault detection, detection to recovery mechanism, fault detection to system restored, fault detection to fault detection. And next, analytical techniques behind DFGs. The power of dynamic fault graphs is unlocked through sophisticated analytical techniques. Here, first, the Markov chains and sophisticated Petri nets. These mathematical frameworks are extensively used to quantify various dependability metrics, allowing for precise probabilistic analysis of system states over time. Numeric methods. Numeric methods. Example uniformization. Efficient numerical methods such as uniformization are employed for quick and accurate transient and steady state analysis, providing insights into system behavior under evolving conditions. And next, the regenerative point techniques. These techniques are vital for evaluating the economic implications of repair and recovery processes, helping to balance system reliability with operational costs. And next, case study fault tolerant multiprocess systems. We modeled a fault tolerant we modeled a fault tolerant multiprocess systems using a DFG, meticulously capturing transient faults, latent errors, and automatic recovery mechanisms. The analysis revealed optimal redundancy levels, striking a crucial balance between system cost and recovery reliability. The case study effectively demonstrates how DFGs can guide critical design decisions, directly leading to significantly improved system availability. And here in the diagram, we can see the fault tolerant multiprocess system, which have the carry memory and other things like reducence process, error detent correction, memory modules. Benefits of using dynamic fault graphs, DFGs. They provide a more accurate representation of real world faults behaviors compared to traditional static models, offer robust support for hierarchical and modular system modeling, enabling analysis of complex multi-layered ar- architectures, significantly facilitate dependability testing by precisely identifying critical fault combinations and sequences. Current research and future directions. Integration with layered network concepts. Exploring how DFGs can be combined with layered network models to enhance dependability, test selection, and efficiency. Fault injection experiments for validation, combining DFG models with practical fault injection experiments to validate theoretical predictions and refine model accuracy, extending models to emerging domains, adapting and applying DFG methodologies to new and evolving computer environments, including embedded real time and cloud systems, to address their unique dependability challenges. Conclusion. Building trustworthy systems with dynamic fault systems, graphs. Dependability analysis is not merely an option, but an essential requirement for the development of mission critical fault tolerant systems. Dynamic fault graphs provide a powerful and flexible modeling framework that accurately captures the integrate behaviors of complex systems under various fault conditions. By leveraging these advanced tools, We can systematically design and build computer infrastructures that are not only safer and more reliable, but also inherently more trustworthy. Thank you.